Okay, in this chapter we study Hamiltonian mechanics. Until now we studied the Newtonian mechanics based on the Lagrangian approach. Lagrangian approach is based on the fact that Euler-Lagrange equation is equivalent to the Newton's equation of motion. The Newton's equation of motion is written directly from F equals ma. However, the Euler-Lagrange equation can also be derived from the action principle. The Hamilton's least action principle states that the action, that is the time integral of the Lagrangian, the action is minimized if a mechanical system follow a physical path, and that is the action is minimized along that path. The Euler-Lagrange equation is exactly the same as the Newton's equation of motion, that is the second order differential equation. On the other hand, we can also obtain the equation of motion based on the Hamiltonian mechanics. Hamiltonian mechanics is derived from the Hamiltonian. And actually, we have already noticed that the Hamiltonian is the kinetic energy plus potential energy when the potential is independent of explicit time dependence and the velocity independent. In that case, according to the derivation for the second form of the Euler-Lagrange equation, the total time derivative of the Hamiltonian was the same as minus partial time derivative of Lagrangian. In this chapter, we construct a formal way to find out the Hamiltonian of a system. The starting point will be the Lagrangian. The transformation from the Lagrangian to the Hamiltonian is called the Legendre Transformation. Let us first learn some terminology regarding the Legendre Transformation. First, a function is convex. Function is convex with respect to a variable. Especially we are interested in the variable x dot. The reason is that the kinetic energy, and in the Lagrangian, the kinetic energy expressed in terms of x dot. So x dot appears in the kinetic energy, and the dependence of the velocity x dot on the Lagrangian is to be replaced with the canonical momentum, also called the conjugate momentum, corresponding to the coordinate x. So, first of all, this is convex. Convex function has it's a derivative increasing as this variable increases. And concave function, which has the local maximum, its derivative decreasing as x increases. We are interested in the function convex function. The reason is that our kinetic energy for example, in the non-relativistic case, both in non-relativistic case and relativistic case, both functions are convex. For example, kinetic energy T is a m 1/2 mx dot square. That is this kind of form as x dot is the horizontal axis. Its derivative is increasing. That can be found by taking the derivative this is the slope. Slope is increasing. And the minimum value, in that case, there is a local minimum value. That is the case. This slope becomes 0. To determine whether it is a convex or concave, we take another derivative with respect to x dot. Then we have m, mass m, that is a positive. So our kinetic energy, non-relativistic kinetic energy, is a convex function with respect to x dot. Next, we consider a Lagrangian, which is a function of velocity and the coordinate. It's a convex function of x dot, right? Our non-relativistic Lagrangian is a convex function, because we are considering a velocity independent case. Lagrangian for the non-relativistic case, this is m and this positive definite, so convex function. Next, we first draw the original function on the x dot y plane. This is x dot and y, vertical axis is a y-axis, and this is a function. This is a convex function. This is y. Actually, this is a Lagrangian. All right. Then we plot a straight line. This is a straight line coming from the origin. Then we define this kind of function. This is a function of x dot, and this is a function of a slope of this straight line. So this function is a straight line minus Lagrangian. Straight line minus Lagrangian. So actually this is a function of the slope, horizontal axis, and because Lagrangian is also a function of x, this is this. All right. So this f function is the distance between this straight line and the kinetic energy curve. We define x dot p, where this capital F becomes a maximum value. Because it's a concave and it's a straight line, the maximum value of this function can be obtained by taking the first partial derivative with respect to x dot. Here, that x dot becomes the derivative of f with respect to x dot becomes 0. The value of x dot at which this f function is maximized is called x dot p. And when we substitute this optimal value for the x dot into the f function, what we obtain is the Hamiltonian. And actually this is a Hamiltonian of function of p and x. That is f of p x dot is replaced with x dot p and x. X is for the coordinate, the potential energy. Alright, this transformation from the Lagrangian x dot x is transformed into Hamiltonian p comma x. This is a transformation called Legendre transformation. Okay. The summary is here. Lagrangian. We have a Lagrangian which is a convex function with respect to x dot, which has the minimum, and we draw a straight line passing through the origin with the slope p. Y equals px dot. It's a slope p. We draw a straight line and subtract the Lagrangian from this, and you will find the difference. And what we want to find is the maximum value of the difference of these two functions. And at the this difference becomes maximum when x dot is x dot p. Okay, x dot p can be obtained by taking the first order partial derivative with respect to x dot of f. When we substitute this x dot into the function f, we find Hamiltonian, and the transformation from the Lagrangian to the Hamiltonian is called the Legendre transformation. Alright. So f function, that is a px dot minus Lagrangian, it varies depending on x dot, and it becomes the maximum value when x dot is replaced with the x dot p. The value of x dot p can be obtained by taking the partial derivative of this f function. F is a px dot p, and in the non-relativistic one-dimensional point-like particle case, px dot minus kinetic energy plus potential energy. Here we assume that the potential energy is independent of velocity. Alright, so this one becomes the maximum value when we take the partial derivative with respect to x dot. The partial derivative of f with respect to x dot is p minus mx dot, and then potential energy is independent of velocity. We consider the conservative force independent of velocity and independent of time. Thus, what we find is, and actually mx dot, this one is the conjugate momentum with corresponding to the coordinate x. Therefore, we find that mx dot must be the same as the conjugate momentum. So x dot p is the conjugate momentum divided by m. If I substitute in here, what we find is, in one-dimensional case, f p x dot p x equals, that is the Hamiltonian, a function of p and x, equals px dot, x dot is replaced with p over m minus 1/2 m p over m squared plus potential energy. Therefore, p squared over 2m plus u of x. This is the final result for the Legendre transformation of a one-dimensional motion of a particle under a conservative force. If we extend this method to the three-dimensional case, our Lagrangian is 1/2 xi dot squared minus potential energy, right? So by making use of this Lagrangian, we construct the f function. F function becomes we have to sum over all three indices, p1 x1 dot, p2 x2 dot, and p3 x3 dot. All right, and then we have minus kinetic energy plus potential energy. All right. Again, to find out the xipi, that means the value of x dot I, the value of x dot I, then maximize the f function. All right. The value of xi dot can be found by taking the derivative of this f function with xi dot. If I do that, it becomes pi, and this one is erased, mxi dot, and the maximum condition is equal to 0. Therefore, this xi dot pi is the pi over m. If I do the same job for the three-dimensional case, the result is quite similar. Pi, xi, f, pi, xi dot, p, I, xi equals pi, pi, and xi dot is replaced by pi over m, and 1/2 m. Xi dot is a pi over m squared, and the potential energy. If I add this up, this is a 2m over p vector squared plus potential energy. Okay, so this is the Hamiltonian for the final result for the Legendre transformation of the Lagrangian of a point particle moving in one dimension. Okay. So in summary, the Legendre transformation is, first, write down this f function as a sum of pi xi dot subtracted by the Lagrangian, and find out the maximum value for this. And the condition is that the first order partial derivative is with respect to p xi dot is pi, and first order partial derivative with respect to xi dot is just okay, equals 0. And we were able to express in terms of this is mxi dot for the non-relativistic case. Therefore, xi dot equals pi over m, right? Once this value, this is x dot ip, xi, this f function has the maximum value when xi dot is replaced with pi over m. As a result, we were able to find out the Hamiltonian for the three-dimensional particle, three-dimensional motion of a particle. Next step is to derive the Hamiltonian for the relativistic case. Before we go further, we simply summarize what we have done. F function, the Legendre transformation is first step is a construct a F function. That is p dot x dot p dot x dot subtracted by Lagrangian. This is the three-dimensional case, and this is the one-dimensional case. We recall that P is the conjugate momentum, but in here, this one gives x dot is to be replaced with P over M. All right. In the case of the potential energy, which is independent of the velocity, this one can be directly obtained by taking the partial derivative with respect to coordinate time derivative on the kinetic energy. All right. At the end of the day, the Hamiltonian was obtained in this way. So, if the energy is independent of expressed time dependence and is independent of velocity, the Hamiltonian is exactly the same as the total mechanical energy. But Hamiltonian is must be expressed in terms of momentum and coordinate. So x is the coordinate and p is the momentum, that the conjugate momentum corresponding to the coordinate x. Pi is the conjugate momentum corresponding to the coordinate xi. Next step is to find out the Hamiltonian for the relativistic case. We first the Lagrangian of a free particle in the relativistic theory is this one. Where xi dot is dx over dt. That is the velocity. Remember, this time should be dilated time. This is proper time. This is the Lagrange factor. And beta is the absolute value of x dot divided by the speed of light. Okay? All of you must be familiar with these relations. All right. And actually, action, this must be Lagrange scalar, and action is this kind of form. This should be Lagrange invariant. However, we know that time is dilating with the factor of gamma. Therefore, we have proper time integral multiplied by gamma L. This is proper time integral. Because it's proper time integral, gamma L must be Lagrange invariant. In order to have our action to be Lagrange invariant. As a result, we have gamma L Lagrange invariant. So gamma L is a Lagrange invariant. Is there any Lagrange invariant quantity for a particle of rest mass m? 0. m0 is the rest mass. L is of dimension has the dimensions of energy, and Lagrange invariant energy of a particle of mass m0. The only possible way of describing this one is the m0c squared. Particle which is not moving, the only constant that is available to have the scale of energy is mass multiplied by velocity, and invariant velocity in the world is just the speed of light only. So gamma L must be m0c squared multiplied by some constant. Alright, so Lagrangian should be of the form lambda m0c squared, and we know gamma equals 1 minus beta squared. Therefore 1 over gamma is square root 1 minus beta squared, and beta squared equals x dot squared over c squared. Therefore if I substitute it in here, I have lambda square root m0c squared. If it is right, it must reproduce the non-relativistic theory. If beta is very small, we can make an expansion. This is beta squared. So Lagrangian should be lambda 1 minus beta squared 1/2 m0c squared. This one is 1 minus 1/2 beta squared. Beta squared is c squared over x dot squared m0c squared. This is lambda m0c squared minus 1/2 lambda c squared cancel m0 x dot squared. Non-relativistic Lagrangian, free particle Lagrangian is actually we have 1f m0 x dot squared. Aha, so lambda equals -1. Therefore, this is the correct expression for the Lagrangian, not relativistic Lagrangian for free particle. Okay. Using this Lagrangian, let us compute the Hamiltonian. Hamiltonian computation is carried out by Legendre transformation. First, write down the f function. F function is p dot x dot minus Lagrange. We first find out the conjugate momentum pi. The conjugate momentum pi is the partial derivative of the Lagrangian with respect to coordinates time derivative. If I take this derivative, I have m0c squared. Derivative by chain rule, we have this is square root is power is 1/2. So, and if I take this one partial derivative with respect to xi dot, we have minus two xi dot over c squared. Now 2 cancels, minus minus becomes a plus, c squared cancels, and our final result is m0 xi dot square root 1 minus c squared x dot square. This is the conjugate momentum. If I substitute this conjugate momentum here into here, before we do that, what I need to do is find out the maximum value for the function f. That maximum value of this function is the Hamiltonian, and that is to be replaced with x dot equals x dot p. What is this? This one can be obtained, this relation can be obtained by solving this equation. Right? So let me move this one to the left hand side. For the time being, let us replace x dot with beta. First, square this. P vector square equals m0c squared beta squared, right? Because of this xi dot equals c beta, right? And then this is 1 minus beta squared. So p squared 1 minus beta squared equals m0c squared beta squared. This one can be moved to here. We have p squared equals p squared plus m0c squared beta. Therefore, beta squared. So beta squared equals p squared plus m0c squared p squared. We know that pi is proportional to xi dot. So p is proportional to x. So by taking the square root, we find that equals, this one is this, so we have pc over square root p squared plus m0c squared, and this is the value for x dot I p. So now we are able to substitute this one into this expression. F equals p dot this one, pc square root p squared m0c squared, and Lagrangian is minus plus m0c squared and square root 1 minus beta squared. Where is 1 minus beta squared? 1 minus beta squared. Here. 1 minus beta squared. 1 minus p squared okay. Combine these together, and this is p squared c this one is M0CC. And if I multiply this one in the numerator, it's a p square cancels and M0C square survives. If I combine the denominators, we have NC, and they cancel to find and if we can insert C inside. Like this. And this is expressed in terms of P only. Therefore, our Hamiltonian for a free particle is this. So you have to remember variable for the Lagrangian and Hamiltonian for the relativistic free particle. We must know this to carry out the further consideration for the relativistic interaction. Alright, until now we have studied how to determine the Hamiltonian out of the Lagrangian. The Hamiltonian is the Legendre transformation of a Lagrangian. Legendre transformation of a Lagrangian can be obtained by first getting the f function. F function is momentum multiplied by the velocity subtracted by the Lagrangian, and then find out the value, find out the maximum value of the f function at which maximum value, and the maximum value is to replace the mass times the time derivative of coordinate to be the momentum p, conjugate momentum p. Thus, in the non-relativistic case, it was Lagrangian was expressed in terms of x dot and x, that is 1/2 mx dot squared minus u of x, and corresponding Hamiltonian was p squared over 2m plus potential energy. In the relativistic case, the Lagrangian was obtained like this by taking into account the Lorentz invariance of the action and expansion of the Lagrangian in the non-relativistic limit, reproduce the Lagrangian for the free particle Lagrangian for this. Here, m0 is the rest mass of the particle. By making use of the Legendre transformation, we were able to find out the Hamiltonian of the relativistic free particle system that is exactly the same as this. And this method is also true for the generalized coordinate system, and we consider mechanical system. Suppose that we have many particle system even, and in case we have n generalized coordinates qi, then the generalized momentum pi can be obtained by taking the partial derivative of qi dot for the Lagrangian. And once you know this conjugate momentum, or so-called canonical momentum, then you can construct the f function. f function is this canonical momentum multiplied by the coordinates time derivative, and then subtract the Lagrangian. The maximum value of this f function is called Hamiltonian. The value of qi dot at which this f is maximized can be obtained by taking the partial derivative of this f function with respect to qi dot, and from which we can find the relation for replacement of qi dot with momentum. Based on that, we can obtain the Hamiltonian for in generalized coordinate system. What we have done until now was the single particle Lagrangian to Hamiltonian in the non-relativistic case, and single free particle Lagrangian for the non-relativistically moving particle of Lagrangian, and carry out the Legendre transformation to find out the Hamiltonian of the system. Okay, let's review what we have done until now. All right. We can do some more. In the case of Euler-Lagrange equation, we had this kind of form. This is the Euler-Lagrange equation for the generalized coordinate. And here, this is actually the, what is that? This is actually the conjugate moment. So this is a pi dot, and right hand side is a partial derivative of Lagrangian with respect to the generalized coordinate. Now we are interested in find out the equation of motion in the Hamiltonian formalism. One must remember that in the Lagrangian case, if we apply the action principle, we vary the action, and if we vary the action, we vary the Lagrangian. If we vary the Lagrangian, we vary the coordinate and the time derivative of the coordinate. And the time derivative of the coordinate, delta qi dot, was defined to be the time derivative of the variation of the coordinate. However, therefore, this one, qi dot's variation is completely determined with qi's variation. That's the reason why we had a single variation along qi, and that was this second order derivative appears because of this relation. Right? You remember, if I vary the Lagrangian, partial derivative with respect to qi and variation of dq plus qi dot L delta qi dot, and it was this, and we replace this. So right, and then variation of delta qi multiplied by, subtracted by, and then combine these two, because at this point this one is momentum, actually, pi, right? Momentum pi, and momentum pi was in case the Cartesian coordinate is mxi dot, something like that, right? We have the first order time derivative. There is no second order time derivative. However, when we move this guy outside, it produces the second order time derivative. That's the reason why we have a second order time derivative, and the variation is along q only, and qi variation is independent. Qi dot variation is depending on the qi variation that is completely determined. However, in the case of Hamiltonian mechanics, the variation of p and variation of q are independent. It is because we have introduced the Legendre transformation. When we introduce the Legendre transformation, we draw a curve. This is Lagrangian that depends on x and x dot. And when we draw a straight line, this straight line introduces parameter p. That is, finally we end up with the conjugate momentum. But this slope of this is a free parameter. It's independent of the Lagrangian. Even though they are correlated at the end of the day, this p is independent of coordinate. Xi's variation was possible, xi dot's variation was possible to be obtained from the x variation time derivative, but it is not in this case. Therefore, we expect that this kind of double time derivative does not appear in the Hamiltonian case. At the end of the day, you'll find the Hamiltonian equation is not a second order differential equation, but a coupled first order equations, two equations. Each of them, one of them is along the variation of q, and the other one is according to the variation of the corresponding conjugate momentum pi. Let's see. Hamiltonian, let's find out the total differential of the Hamiltonian. And total differential of the Hamiltonian can be made, this product, so first differential and second differential, and minus Lagrangian. Lagrangian's differential is through coordinate q, through velocity. And perhaps it may have some pure time dependence. And this one is copied in here. As we know, pi is conjugate momentum. Pi is the conjugate momentum. And first of all, this one appears here, this one appears here, and then here dqi appears here, but we replaced I with j here, right? And then where is the dq dot? Here is our dq dot. Dq dot is here, so they are combined. This one and this one are combined in here, and time derivative appears here. All right. dqj, this total differential dqj has the factor. This by definition cancel. This pj is the conjugate momentum, and this is exactly the same. The only contribution appears p and q and dt. From this expression, what we find is, from this equation, we can read off this q dot and p dot. Okay, let us discuss later. Okay, we were considering the Hamilton's equation. We return to the f function before we substitute the qi dot with the qip. The total differential of the Hamiltonian is a total differential of the f function, that is a pi qi dot minus Lagrangian. The total differential of a product is differential of p and differential of q dot and multiplied by the other vector. So dpi qi dot, pi dqi dot. And Lagrangian depends on q dot, and perhaps t. So minus partial derivative with respect to qj and multiply the differential of qj, and partial derivative of with respect to qj dot multiplied by qj dot differential, and partial time derivative and multiplied by dt, where ij's are all summed over. And I copied this dp vector in here. This is qi dot, and next one the dp and dq vector. dq term is this one with force related term. This is Lagrangian's partial derivative with respect to coordinate. And then there are two pieces that depends on qi. So if I combine them with the qj, I can replace this index for momentum with j. So pj and minus Lagrangian's partial derivative with respect to qj dot, and then time dependent piece. Alright, however, this one is just definition of the canonical momentum. Therefore, this one is exactly 0. So if we consider momentum p, then after Legendre transformation, the differential involving the velocity of the coordinate disappears. Therefore, we end up with the expansion in terms of momentum differential, coordinate differential, and time differential. And now we replace this one with the we can make use of Euler-Lagrange equation, round qj round L minus dt d round qj dot round L equals 0. We know this is qj equals time derivative what? This is conjugate momentum pj. So pj is here, and total time derivative of pj is pj dot. So I can insert this one in here, and this is our master equation, from which we can read up many things. If I take the partial derivative with respect to pi, I have round Hamiltonian's partial derivative with respect to pi equals qi dot. And then next one, Hamiltonian's partial derivative with respect to qi equals minus pi dot. These two are called Hamilton's equation of motion. And then from here, partial time derivative with respect to time, a partial time derivative of Hamiltonian is minus Lagrangian's partial time derivative. And then one more piece. We know that this one is the total time derivative of Hamiltonian. This is second form of Euler Lagrange equation. And this one can be obtained from this relation. Alright. We compare this. And here we previously obtained dH is qi dot dpi minus pi dot dqi minus Lagrangian's partial time derivative with this. And here, because h is a function, Hamiltonian is a function of p, q, and possibly t, if I compare these, we again obtain this is called the Hamilton's equation of motion or canonical equation of motion. So let us consider the Hamiltonian of the non-relativist case. With velocity independent potential energy. What is that? That is this one. And if I make use of the Hamilton's equation, because of this, this is Cartesian. Hamiltonian's partial derivative with respect to qi is potential. Not always true, because if it is generalized coordinate, this momentum may have a coordinate, so let's just leave it as it is. Just Cartesian. Cartesian case, this is x, x, and potential. And actually this is minus of Lagrangian, right? And this is pi dot if I make use of Lagrangian, right? So negative sign. That is equivalent to this result. Okay. For example, we consider the simple harmonic oscillator. P. That is x dot. X derivative kx. That is minus kx, right? And that is minus p dot. We have two coupled coupled equation. P equals mx dot and p dot equals minus kx. P dot equals actually force. If I insert this equation into here, I have x double dot plus kx. Where okay. We can consider Hamilton's equation for various cases. For example, we have a Lagrangian in the 2D polar coordinate system. Lagrangian is a kinetic energy. Minus potential energy. And then conjugate momentum. Conjugate momentum for theta. Hamiltonian is does here r dot equals to PR over M, theta dot equals P theta over MR squared. We have PR P theta over MR squared P theta and plus squared this plus our theta. We have PR squared m minus 1/2 PR squared over m. We have P theta squared mr squared minus 1/2 m squared m r squared r to the 4th, so r squared p theta squared plus potential energy. Therefore, what we have is PR squared over 2m plus p theta squared over 2mr squared plus u r theta. The equation for Hamilton's equation, there are 4 Hamilton's equations. Round H, round PR. Here, PI's derivative is QI. First, we carry out this calculation. This PR over M equals R dot. Right? And round H over round R, that is here P theta squared minus mr cubed, right? And then plus round r u equals minus p r dot, right? And then momentum p theta mr square, that is p theta mr square, that is theta dot. Hamilton's equation for theta dependence only appears here. Potential energy equals minus p theta dot. We have a 4 first order differential equation. Those are Hamilton's equations. All right. And then we might want to consider many other cases. The spherical polar coordinate system will be very complicated, but you can do that. Look into this. In case we have some constraints, if we have some constraints, then we introduce Lagrange's undetermined multiplier But Hamiltonian mechanics, in the Hamiltonian mechanics, we can also apply the condition, and this relation can be used for the minimizing the action. In addition, we remember Hamilton's equation is just like that. If I add any constant to Hamilton's equation, the Hamiltonian, this is 0. We just multiply sigma a, lambda a, fa. It is just 0. What I do is just add this 0 to Hamiltonian, and that does not make any difference at all in the final result. And then by making use of this, we can vary pi and qi independently. Because of that, the substitution of this one into this expression, substitution of this relation into this relation, what we get is this one is the same as the original one, but we have this one plus sigma lambda a fa plus sigma a lambda a fa. By adding this, we can modify the equation. This one becomes this one. Differentiation is with respect to pi. This equation, if I move this one to the left hand side, what I get is this one on the right side. Alright. Let me check it. If I think it should be negative sign on it. Negative. It should be a negative sign on it. Okay. All right. So this method can be addition of the Hamiltonian by a constant. By a constant, we can derive the equation of motion for the constraint system. And the total derivative, let's see, we have h dh round pi round h dpi h qi dqi total time derivative is pi dot qi dot this is applying the chain rule, and Hamilton's equation states that this is pi. Hamilton's equation, pi derivative, that is qi dot. Hamilton's equation for q derivative, this is minus pi dot. We have qi dot plus partial derivative. Okay. Therefore, this one cancels. Hamiltonian's total time derivative is the same as Hamilton's partial time derivative. And we recall that this is partial time derivatives of Lagrangian multiplied by -1. Okay, this is our final result.